Hello everyone. So now we are going to discuss an important chapter called Moving Charges and Magnetism. So this is a very important chapter in your class 12th part 1 and also a lengthiest chapter. But trust me, after watching this video, you will feel very easy because I have just compiled everything starting from the first topic to the end of the topic. The notes I have just made. This is my own notes. So these notes I have just taken from NCERT textbook and a famous textbook called SL Arora. Okay. The famous textbook, a reference book SL Arora, and my coaching notes. Okay. So by combining these materials only, I have just made my own notes for my own notes. So with which I got a good marks in my class 12th as well as in mains. So let's start this chapter. So what is moving charges and magnetism? It's completely based on the magnetic field. Okay. Basically, if you have a current carrying conductor, okay, it will produce a magnetic field out of it, due to which it will exert some magnetic force. So this is the whole concept discussed in this chapter. Okay. So magnetic field means what? A space around a magnet within which its influence can be experienced. Yeah. If you keep a magnet in a space, it will exert some magnetic field, right? So that's what the magnetic field. Magnetic phenomena. You can just read the theory points. Okay. Magnetic force means what? A static charges produce electric field, current moving. Yeah. In first chapter electrostatics, you might have seen a charge which is kept at a plane which is not moving. So that's called static charge. So that produce electric field out of it. Right? Electric field. This is electric field. But if anything charge, if it is moving, if it is in motion, then it produces some current, right? So current means what? Charge moving, right? The basic definition of current. Charge will be moving. So in that case, in addition to the magnetic force, magnetic field will be produced. Okay, that is vector. That magnetic field's property is vector. So magnetic field means what? Defined at each point in space, addition to depend on time. So it obeys a superposition principle. So these are the theory points. You can just note it down. So this is Boyd-Servet law. Magnetic field due to a current element. So if you have a small current element, let's say, okay. See, this Boyd-Servet, a scientist, got an expression for magnetic field of a current element. So let's say you have a current element dl. Okay. What is the magnetic field produced by this dl element at any particular general point? Let's say point P. That's what I've written. The relationship between the current and magnetic field it produces. So you see, the main thing is the relationship between the current and the magnetic field it produces. In starting itself, I have just mentioned, right? Any conductor which is carrying current, it will produce a magnetic field, it will exert some force. So these are the very important basic points with which this chapter carries. So let's take a point P where a magnetic field due to this current element at this particular point is dB. A small element we have taken, right? dl. That's why the magnetic field also dB. So due to dl element to be calculated at a distance r. So this point we have taken at a distance r from the current element. So r is a position vector. And let's say this dl is making an angle with the position vector theta. Theta is nothing but the angle between the dl vector. This is vector, the direction dl vector and the r position vector. So magnetic field which is produced here at the point P is directly proportional to the current flowing in the conductor. And magnetic field produced at this point P is directly proportional to the length of the conductor and is also proportional to the sine of the angle between them and is inversely proportional to the square of the distance between them. So combining all these things, you can just have a formula. The magnetic field is directly proportional to this entity, this entity, this entity, this entity. So as for removing this proportionality, we can introduce a proportionality constant, okay, k. So that's what dB is equal to k I dl sine theta. So this is the formula. Now k is nothing, depends on the medium between P and the dl. Between the P and the dl, what is the medium? So based upon that medium, the k value changes. So k value, you can just remember mu naught divided by 4 pi. The value is 10 power minus 7 t. Okay, 10 power minus 7 t Tesla. The unit of magnetic field is Tesla. So the name is mu naught is permeability of free space. You might have seen in the first chapter electrostatics. So this formula is very important. Okay, used in many numericals directly. Next, direction. Direction of dBl is perpendicular to the plane of dl. Yeah, of course, because they are mutually like perpendicular in the plane. dl is nothing but in this direction, r is nothing but in this direction, and dl is coming out or going into the paper. Magnetic field. Okay, that's what, or cross, because cross product is nothing but sign we will get, right? So there are some special cases. See, these are the special cases I've just taken from SL Arora textbook. You might not be getting properly in your NCERT textbook, but this notes will be helping you. So if the angle is 0, means sine theta is 0, the magnetic field is 0. So magnetic field is 0 at points on the axis of the element. Means what? If any point is on the axis of this current element, there is no magnetic field induced on it. Only on the side, either on right side or left side, not on the exact axis, there is no magnetic field produced. Okay. Similarly, if the angle is 90°, okay, means what? If it is at exactly like 90° position, if you take any point over here, then the magnetic field will be, the angle will be theta, 90°. Angle will be, magnetic field will be maximum, because sine theta's maximum value is 1. So in that case, the magnetic field produced will be maximum, right? So that's why I've just written the text. So the unit is Tesla. We can just take the unit and derive, okay? Take the value, unit values for all and maximum value for theta. So you'll get 10 power minus 7. Okay. The relationship between mu naught, epsilon naught and the C. Okay, C, the speed value. You know this value 1 by 4 pi epsilon naught is 9 into 10 power 9 from the first chapter, and this value we know. So if you want to get this particular entity, you have to multiply this and this. So you will get an answer 1 by C square. Okay. And C value is nothing but 1 divided by root of mu naught into epsilon naught. This is also a very important formula. Okay. Next. So next, magnetic field on the axis of a circular current carrying loop. So this is a loop basically on the axis. What would be the magnetic field? So this we will discuss later. I have written on next pages. Okay, upcoming pages. So next concept, magnetic field due to a long straight current carrying conductor. See, if you have a straight current carrying conductor, what is the value of magnetic field? Okay, the direction you can assume. You keep the thumb in the direction of moving current, curl your fingers, that will give you the direction of magnetic field induced due to the straight current carrying conductor. You just see this diagram. Is it visible for you? I hope it will be visible for you. Okay, see, this is a straight current carrying conductor. This is the value of current which is flowing in the conductor, and you take any point P over here. Okay, this is a current element dl we are taking, and from this point we are drawing a line. So this is the theta 2 actually. So this is phi 2. Okay, this is phi 1. So the magnetic field due to this particular current carrying conductor, okay, the straight current carrying conductor at this particular point is nothing but mu naught into I divided by 4 pi a into sine of phi 1 plus sine of phi 2. Okay, so a is nothing but the distance between the current element and the point P. So this is the formula, direct formula you have to remember. Now special cases. If the wire is infinitely long, you just imagine it is going very long. So in that case, the angle theta phi 1 and phi 2 will be almost equal to 90°. So that sine theta 1, sine phi 1 and sine phi 2 will be 1 plus 2. So it gets cancelled out. So you'll get the result as this. And if the wire is very long and if this point is lying to any end, particular end, for example here or here, if it is lying at any end, only one angle becomes 90°, other angle becomes 0. So in that case, it will be mu naught I divided by 4 pi a. Okay. Next, this is the most important formula, but very basic formula. Force on a moving charge in a magnetic field. See, in magnetic field, if you keep any charge over here, there will be some force exerted on the charge. So let's take any positive charge q moves with the velocity v in a magnetic field. and the velocity makes an angle theta with the magnetic field. So the charge will experience a force in the magnetic field. So that force will be directly the induced force will be directly proportional to the magnetic field, directly proportional to the charge means, and it will be directly proportional to the sign of the velocity component of velocity in direction of magnetic field. The direction, the angle between velocity and magnetic field. In that case, we'll be taking the sign component of it. There is no derivation means for NCERT level, there is no derivation. Even for mains or NEET examination, there is no derivation needed. So F will be directly proportional to B Q V sin theta. So basically in general form, we will be calling it as QVB sin theta. So this is the force that deflects the charged particle sideways, magnetic Lorentz force. Yeah, very important. So this force is called magnetic Lorentz force. As the direction of the force is perpendicular to velocity and magnetic field. Velocity will be in one direction, the magnetic field will be in another direction, the force will be in perpendicular to it. Okay, velocity will be in this direction, magnetic field will be in this direction, the force will be coming out of the plane of paper or going into the plane, means perpendicular to both of it. So that's why you are taking cross product. So if there is some special cases, if velocity is 0, then force will be 0. Of course, if theta is 0 or 180-degree, means there is no angle, or if it is making 180-degree, then force is 0. Means Q moving parallel or anti-parallel to magnetic field, not experiencing any force. When it will be maximum? When the angle between the velocity and magnetic field is 90-degree, then the force exerted on the charge, the Lorentz force, will be maximum. Okay, next. There are some rules for finding the direction of force on acting on the charge Q. You can use Fleming's left hand rule, right hand palm rule. Okay, you can just research about this Fleming's left hand rule, right hand palm rule, using the palm. Okay, I cannot draw this hand properly, you can just research about it. So these are the dimensions of magnetic field and dimensions, and sorry, unit. This is a unit 1 Tesla, and 10 power minus 4 Tesla is 1 Gauss. Okay, you have to remember this. And dimension, of course, from kinematics, the basic units. Dimension you can just find like this: force has mass into acceleration, Q current into time, charge. Okay, what is current? Charge flowing per unit time. That's what current in time, and V velocity, mass into sorry, meter per second, and sin theta there is no, so constant to 1. So this is the dimension. So Lorentz force means what? The total force Q. Okay, Lorentz force. So with that we have seen magnetic Lorentz force. Now the general term Lorentz force means what? If anyone is asking you what is Lorentz force, that's nothing but the total force acting on a charge where electric field is also present as well as magnetic field is also present. That's the total force, nothing but Lorentz force. Let's say a charge Q in electric field experiencing an electric field. So due to the electric field, there will be an induced electric force. Force is equal to QE. This formula also coming from electrostatics. And there is also a magnetic field, right? So due to magnetic field, there will be some force acting on the charge if the charge is moving with a velocity v with some particular direction. This is the magnetic force. So combining these two, we will be getting the complete force. This is Lorentz force. QE plus QVB sin theta, taking Q common. Okay, next. See, yeah. Force is equal to ILB. This is also one of the important formula. That derivation I have written over here. Okay, derivation is not needed for any competitive examinations, but for NCERT, for board examination, you need to know. Force on a conductor. See, if you have a conductor, okay, if you have a straight conductor with a length L, if it is moving, if it is having a current, means if I current is flowing in the conductor, there will be some force exerted on it. In case, provided if it is kept in a medium of magnetic field, okay, B magnetic field, if it is kept, then there will be some force exerted. Let's see. Let's take a conductor of length L, okay, and area of cross section carrying a current I. Exert magnetic field V acts on it. So, sorry, external magnetic field acts on it. So there will be some external magnetic field because we have kept in a magnetic field medium. So for steady current I, each electron has an average drift velocity. So these are all the things which have the concepts are coming from current electricity. So each electron experiences a force. Okay, QVB, but the Q charge here to electron. So negative charge, drift velocity V into magnetic field. So N is nothing but number of electrons in unit volume, total number of electrons in a conductor. So this is for unit volume, but we have the volume what? Current. Okay, N is nothing but for unit volume, one unit volume. This is the number of electrons, but for the whole volume, area of cross section into length will give you the whole volume of the conductor. So multiply this with N will give you the total number of electrons in the whole conductor. Okay. Next, total force on a conductor. What is total force? What is the total force? So this is the force exerted on a single electron, but we have these many number of electrons. So that's what N into that F value. Okay. This is the force exerted on a single electron. We have these many number of electrons. So multiply these two will give you this entity. So you take E common outside, L into V cross B. So I hope it's visible. So take the drift velocity outside. So L cross B. So this entity ENAVD, okay, ENAVD is nothing but I from current electricity chapter. So that's what F is equal to I into L cross B. You want I will write. F is equal to I into L cross B. ILB sin theta. Oh, sorry. Yeah, ILB sin theta. Okay. This is the force exerted on a conductor. Okay. So similarly, there are some special cases. If theta is 0, 180, you will be getting 0. And if it is 90 degree, means perpendicular, you will be getting the maximum force exerted on it. And this is one of the very important thing. If you, there are many chances you can get any theory question based on this particular concept. Motion of a particle in a magnetic field. See, in presence of magnetic field, if a particle is moving, there are many things in terms of kinematics happening. See, when velocity is parallel, theta will be 0. In that case, there is no force acting on it. If velocity is parallel to the magnetic field, there is no force acting on it, right? If, let's say, if you have magnetic field in this direction, if the charge is also moving in this direction, there will be no force acting on it. Okay. But if the velocity is perpendicular, if the velocity of the particle is perpendicular to the magnetic field, then there will be some angle theta, which is 90 degree. Then in that case, maximum force will be acting on the particle. Okay, that's what maximum force. But this force can change the direction of the particle. Okay, very important. Can change only direction of moving charge. The magnitude of the particle will not change. Means the velocity will not change. The direction will change. If magnetic field is perpendicular, there will be no work done. No change in kinetic energy because velocity remains constant. Only the direction is changing. Direction of momentum may change, but there is no change in kinetic energy because there is no change in velocity. Velocity to remain constant, right? Note, electric field means Q into E can have component parallel non-parent to motion, thus can transfer energy in addition to momentum. Because of the electrical field, transfer of energy can also be taken place because momentum to that will be provided by magnetic field. Okay, but transfer of energy can be provided by electric field, the force QE. So this is very important. Make a note of it. You see, this case. This is the magnetic field acting going into the paper. We have a charge Q over here. If the velocity of the charge is in this direction, continuously the direction of the force, sorry, direction of the velocity of this charge will get deflected. So the particle eventually follows a circular motion. Okay, this force deflects particle continuously sideways without changing its speed. So the speed of the particle will remain constant, but the direction will change drastically. Continuously, the direction of the velocity will, direction of the charge will change. So eventually, it follows a circular motion. That's what. Q moves along the circle perpendicular to the magnetic field. Okay, magnetic force provides. Now here's this interesting formula. What force is making this charge to move in a circular manner? Centripetal force. from circular motion chapter from 11th, we can say if any particle is moving, means any particle is under a circular motion, there will be some centripetal force which is seeking towards the center, right? If you have any material which is moving in a circular manner, there will be some force seeking towards the center, right, in a radius r. So that's what mv square by r I've written. Center. So this, see, if any particle is under a circular motion, there will be some force, centripetal force seeking towards the center with a radius r. So that's what. These force must be equal QVB. This is the magnetic force acting on the particle as it is moving in the magnetic field. So as it is in a circular motion, there will be some centripetal force acting on this particle. So these two forces must be equal. So after equating, we'll be getting a radius formula, one of the very famous formula. Remember it. And time period T is equal to pi r by V. You substitute it, you will get the relation, and frequency to 1 by time period. Some special cases when theta makes an angle with V in a uniform magnetic field, okay, acting in the x direction, a Q is projected like this with an angle making theta with the magnetic field. So there, what is the parallel component? This component is V cos theta, remains unaffected because that is in the direction parallel to it. But the perpendicular component of the velocity V sin theta will experience a force. That's what QVB sin theta. So this force acts perpendicular to this, makes charge to move in a circular path. This is the path generated by the particle, okay, like this in a zigzag manner. The reason why the charge is moving like this continuously, as the charge is being projected like this, it has some parallel component and perpendicular component. This parallel component is remain unaffected because this is parallel to the magnetic field. But this velocity Vt is perpendicular to the magnetic field. Magnetic field is in this direction, right? So continuously there is some force, magnetic force is acted. So continuously it's get deflected like this. So eventually there will be some spiral pattern the charge is following, okay? So that's what. In this diagram, you can just view it from NCERT textbook, okay? It will be clearly given. That's what the charge to makes charge to move in a circular path along YZ plane. Radius mv by qb, you can just substitute this Vt, and time period 2 pi r by Vt. Everything here, the velocity, perpendicular velocity. Now see, a particle Q in a uniform magnetic field has only two motions, a linear motion along the x-axis. It can move in a linear manner or it can move in a circular manner. So combining this linear motion as well as the circular motion, okay, sorry, as well as the circular motion, we have seen a particle can move in a circular motion or in a linear motion, right? So combining these two things, that's how the helical path, the shape is known as helical. That's why the helical shape attained, okay? These are a very theoretical concept, okay? You should know why the path of the particle is helical, how it is because of the linear motion as well as the circular motion. Combining these two things, the particle is moving in a helical shape. And the linear distance moved by the charge in this direction of magnetic field in one revolution. In one revolution, what is the linear distance it's covered? See, in one revolution, what is the linear distance is covered? What is the distance? See, basically, see, distance into time. Distance means what? Speed into time. Speed v cos theta. This is the linear velocity, and the time period in you are multiplying. V cos theta into t will give you the pitch actually. Now, another important formula. Okay. Magnetic field at a center of a circular current carrying loop. So if you have a loop which is carrying a current I, what is the magnetic field at the center? Okay, you just curl your fingers in the direction of loop current. Okay, you just take your right hand, curl your fingers. Your thumb will point into the page, right? So that's the direction of magnetic field. You take any circular loop of radius r. need to calculate magnetic field at the center of the loop. So we are considering a small dl element over here. Okay, dl element, magnetic field at the point O due to this dl element, void surround law, what we have seen, mu naught I divided by 4 pi into dl into r divided by r cube. So this is a position vector. They are multiplying one position vector divided by unit distance. That's why r cube came, nothing else. Or you can just ignore it and keep it as r1 by r square itself. So dl is perpendicular to the radius, taking sine component as it is perpendicular, right? So sine 90 is 1. So mu I divided by 4 pi into dl by r square. So this is the magnetic field produced due to the single small dl element. Similarly, magnetic field due to all such elements, what we'll do in physics or mathematics, what we'll do in science, if you take any small dl element, if you want the whole part due to the complete ring, you will integrate it. So eventually you will, from upper limit from 0 to the complete length of the conductor, if you integrate it, you will get B, magnetic field due to the entire conductor. So if you integrate it 1 by r square, everything is constant because you are integrating with respect to the length. So dl, if you integrate the dl, what is the circumference of this? Nothing but length. What is length? Circumference 2 pi r. That's what 2 pi r written. Cancel it. So magnetic field due to a circular current carrying loop at the center is nothing but mu naught times of I divided by 2 times of the radius. That's it. A direct formula you have to remember. Next. Very, very important. Okay. Even in board exam, there may be a chance you may be asked to derive this. Okay. Magnetic field on axis of a circular current carrying loop. See, this is a circular current carrying loop. On the axis, any point you take at a distance x, what could be the magnetic field due to this loop? Sorry, loop. This loop is carrying a current I. Okay, need to find magnetic field at an axial point P. So this is an axial point. So this can be an equatorial point. At axial point P, we are going to find the magnetic field. So this R is the position vector at point P with respect to dl. So we are taking a small element dl. With respect to this dl, with respect to the point, there is a position vector between these two. By Boyer-Saravit law, due to this particular dl element, what could be the magnetic field at this particular point? This is what dB is equal to mu naught times of I dl sin theta divided by 4 pi into r square. Okay. So due to this, you see, due to this current element, there will be some dB force which is acting in this direction, right? In this direction. Due to this dl element, there will be some magnetic force acting in this point in this direction. Both are making some angle theta with the axial axis, right? So this is cos component, this is sine component. Means we are taking with respect to this the angle. So this is cos component, this is sine component. So both cos component will be getting cancelled. So both sine component will get added. Okay. So that's what the field is perpendicular to the radius. Total magnetic field at point P. dB sine component. Only sine component we will take. So dB sine component, whatever the thing you have dB, you substitute over here sine of phi. What is sine of phi? Here, this is the phi angle we are having. What is sine? Opposite by hypotenuse. Capital R divided by R small r. So that's what they have written. And you integrate with respect to the length. dl, if you integrate, you will get the 2 pi r complete circumference. That's what after getting simplified, you will get a formula like this. Mu naught times of I divided by 2 like mu naught I r square divided by 2 r cube. So small r is nothing but x square plus r square the whole power 1 by 2 means root. How? You take the Pythagoras theorem. R square is equal to x square plus capital R square. That's what they have written. Small r they have written x plus x square plus r square the whole root. So this is the formula, you remember it better. This is for a single loop. If you have multiple loops, you just multiply with the value of n number of loops. So some special cases, at the center of the loop, as the value of x is 0, you will be getting an equation. At an axial point far away, if the value is more far, you can ignore actually the radius of the loop. Okay, if the point is very far, actually, so eventually this will be parallel to, means actually it's like going to be like a straight line, right? So you can actually ignore this radius in the formula. That's it. So next topic, Ampere's circular law. Say Ampere circuit law, the basic definition, line integral of magnetic field around any closed circuit loop is equal to the mu naught times the total current passing through the surface. That's it. You just remember this formula, line integral of magnetic field, okay, is equal to mu naught times the current passing through the surface. There is a loop, right? This is C. In a simplified form, if magnetic field is directed along the tangent at every point of a loop, the magnetic field will be constant. So this is for circular loops. Let's see. Only for closed loop. See, consider an element dl. Okay. BDL. The direction of magnetic field will be perpendicular. So as the formula says, it's a dot product. So cos component will be 0. Sorry, cos 0 will be 1. So BDL. Hence, line integral of magnetic field along circular path will be what? If you integrate it, BDL. So if you integrate DL, you will get eventually the length of the conductor. Length means what? 2 pi r. As it is a circular path, 2 pi r. So mu naught times of I divided by 2 pi r into length. Length will be 2 pi r. If you cancel it, you will get the value as 1. Mu naught times of I. So this is the small derivation. There is no actual proper derivation for it, but for my own convenience, from the SL Arora textbook and from my coaching, I've just taken this derivation. If you want, you can just take it out, or else remember this formula. Line integral of B dot dl is equal to mu naught times of I. And this formula we have seen, there is a small proof for straight current carrying conductor from Boyd-Servet law. Means if you have an infinitely long straight wire carrying current, magnetic field due to the straight current carrying conductor at a point R is nothing but from the Boyd-Servet law itself, you can just substitute, you will get this relation. Next, application of Ampere's law. See, this formula can be derived from Boyd-Servet law, even also from Ampere's law. What Ampere's law states? Line integral of BD is equal to BDL is equal to mu naught times of I. Here, boundary of the loop is chosen as circle. Loop is circle. B is tangential to circumference. The magnetic field is always tangential to the loop. Current is flowing in this direction. Okay, it's an infinite straight conductor. Left hand side we have line integral BDL. If you take the cos component, you will have B into DL B 2 pi r. If you equate with the right hand side mu naught times of I, you will get magnetic field is nothing but mu naught times of I divided by 2 pi r. This is for a straight long current carrying conductor. For this conductor, I'm just applying Ampere's law. That's it. Nothing else. Don't confuse it. Now, this is for solenoid. Magnetic field inside a solenoid. Solenoid means what? An insulated copper wire wound closely in the form of helix. Okay, you might have seen. You can just have a look. This is like this. In a helical path, the wire will be wound. This is solenoid. So there will be some magnetic field like this. Okay. Okay. See, the resultant field of a solenoid is a sum of the vector sum of the fields due to all the turns, because each and every turn will have their own magnetic fields, perpendicular and parallel. So the perpendicular component will get cancelled out. Field due to neighboring turns add up along the axis, cancel out in the perpendicular direction. So perpendicular component will get cancelled out. The parallel component will get added up. So if you want to get the complete magnetic field due to solenoid, the sum of all the fields produced by each turn circular loop, if you add all the magnetic field of each circular loops, eventually you'll get the magnetic field of a solenoid. That's it. So theory points you can just read. And now let's come to the formula part. See, this is the solenoid we are having. Okay, I hope it's visible. Solenoid we are having. Now we are going to calculate magnetic field inside a straight solenoid. Inside the solenoid, what could be the value of magnetic field? So this is the formula mu naught times of Ni. N is nothing but the number of turns per unit length. Now let's calculate from the Ampere law. Let's take an ampering loop. You take an ampere circular loop. Okay, name it as ABCD. Okay, this part will be outside of the solenoid. This part will be inside. Now to calculate, consider a rectangular ampere loop. Let left hand side BDL, the ampere formula. Integral BDL is equal to mu naught times the total current. Right. Let's take integral B dl is equal to, we are taking integral from A to B length, one thing, A to B, plus B to C, integral B to C dl, integral A to D, this part we are taking, and C to D we are taking. In this case, this will be 0 because it is outside of the solenoid, so there is no magnetic field produced in it. So this component will be 0. Okay, you can just strike it off. You can just strike it off. There is no need to write this. Now A to B. Now see, B to C is perpendicular. A to D is perpendicular to the magnetic field. Now from the formula, as it is a dot product, cos 90 will be 0. So these two quantity will be 0. Now the only quantity which will be taking is A to B, the parallel component. B dl cos 0 dl. So B into dl. So this is the length. Actually, if you integrate dl from A to B, you will get eventually the length of this solenoid. So L is the length. So magnetic field due to this solenoid, left hand side of the equation from Ampere's law will get B into length. Length is nothing but length of the side AB. Now N is nothing but the number of turns per unit length. This is the length. N is nothing but number of turns. If you multiply these two, you will get total number of turns in this particular length, right? That's what I have written. Now total current is what? If current I is flowing, then for this total number of turns, NL into I. That's what. From the formula, total current is what? N into mu naught into I. Mu naught NLI. So BL is equal to mu naught. If you equate, if you cancel it, you will get B is equal to mu naught times of N into I. So magnetic field at the end of a solenoid, at any end B or D, the half of it. This is at a center, okay, inside the solenoid, this is the value, not center, inside the generally center. And magnetic field at any end point of a solenoid is what? Half of this. Okay. Similarly, magnetic field due to toroid. Okay, this is not that much important. You can just read it out. Similarly, toroid, but the shape will be little tangential. Okay, point in the interior of a toroid. So now let's next see another important and interesting thing. Force between two parallel current carrying conductors. Let's say if you have a one conductor and another conductor. Just imagine, just forget about this. Just imagine if you have one conductor which is having a current, let's say I, A, as the conductor name is A, and another conductor say B, and it is also having a current flowing through it is IB. So if you have any conductor which is having a current A, don't you think so it will exert some magnetic field out of it? So if you keep any conductor nearer to it, so that magnetic field exerted by this conductor will exert some magnetic force on this conductor, right? Due to the field produced by this conductor, if you keep any conductor beside it, it will experience some force due to this conductor. That is what the concept force between two parallel current carrying conductor. Similarly, this conductor will exert some force on this conductor. The reason because it has some current flowing through it and the magnetic field induced because of it. That's what. This is also induced by the ampere. Okay. Conductor carrying current in the same direction attract. And one more thing, this point you remember, if the both of the conductors having that current flowing in the same direction, they attract each other. Just try to remember they are like running in the same manner, so they will just attract each other. If the current is in opposite direction, one is running in this way, one is running in this way, there is no attraction, only repulsion will take place, so repel each other. So let's take two conductors A and B. Current flowing in the conductor A is IA and current flowing in the conductor B is IB, and the distance between them is D, small d. Let's take conductor A. What is the magnetic field due to the conductor A? Infinite conductor, mu naught times of I divided by 2 pi into D. Acting on this particular, let's say point P, acts on point P, any point. It exerts some force on a conductor B. So this magnetic field produced by this conductor will exert some force. So that's what force is equal to ILB. I is nothing but the, you see, carefully listen to this. Now we are going to see the force on conductor B. So for that, the current which is flowing in the conductor B will be taking, and the length of the conductor B we will be taking. But the magnetic field will be induced by the conductor A. This BA will be taking from conductor A. So that's what force on conductor B due to A. Current flowing in the conductor B, length of the conductor, and the magnetic field due to conductor A. So substitute this formula, you will get this equation. Okay. This is very important. Mu naught times of conductor A current, conductor B current, and length of the conductor divided by the 2 pi into distance between them. Direction is towards A, and the direction of the force will be towards the conductor. It's like a seeking force. Similarly, force AB acts towards B. So they are actually opposite direction. So negative sign will be taken. So force per unit length. Unit length, if they are asking, just divide by L. Okay, the length of the conductor, you will get this form. That's what. If both the current direction are in same, they will attract each other. If both are in opposite direction, they will repel each other. Now next. So now see, this is the magnet. So like let's take a small experiment. Two magnet we are having, inside which we have kept a small loop carrying current. Okay, let's say current is going either in anti-clockwise or clockwise direction to take, and length of the each side is A and this B. Okay, as it is a rectangular loop we have taken. Torque experienced by a current loop in a uniform magnetic field. So okay, that's a magnetic dipole actually. So when the loop is placed perpendicular to the magnetic field, let's take the magnetic field is going into the paper and we have kept a loop. Here are the two magnets we are having. So actually what happens here is there is no force experienced on the side AD and the BC. The reason behind is there is no force acting on this side because this side is parallel to this magnet, this side is parallel to this magnet. So no force will be felt by the side of the loop that is parallel to the magnet. Okay, only if it is perpendicular, then only it will experience some force. So only due to the side A, B and C, D, there will be some force, magnetic force. So I, L, B sine theta, because sine component when it is maximum, when it is perpendicular, when it is zero, when it is parallel. So that's why these two sides will not experience any kind of force. So due to the side AB, what is the force? I, the current flowing in this loop into magnetic field, which is passing into the page, and the length of the side AB is small b. Similarly, um, for side CD, what is the force? ILB into small b. So net force, you see, using the right hand palm rule or left hand, like Fleming's left hand rule, if you keep, you will get the direction of force AB in this upward direction, direction of force CD in downward direction. There is no net force acting on this. But if you see, if any force is acting like this, any force is acting like this, there will be some torque, right? Rotational force will be acting. That's what torque. So torque formula is what? Force into the perpendicular distance between from the point. Okay. Force into the perpendicular. For this in center point, what is the value of torque? Force into the perpendicular distance. What is the perpendicular distance? This is the distance A, half of it A by 2. So F1 into A by 2 plus what is this distance? F2 into A by 2. So net torque acting due to this two forces, couple of forces. The definition of torque is what? Couple of forces acting like this. Okay, rotational motion, a rotational effect will be produced. So this loop will be rotating actually. So A by 2, A by 2, if you add it, you will get the value of I into AB into B. What is AB? Area of the loop. That's what A is nothing but area. I into AB, the famous formula. Okay. Case 2, when plane of loop not parallel to the magnetic field, if it is making some angle theta between magnetic field and the normal to the current coil. Okay. If it is making an angle like this, if you see, this is the loop and actually these are the magnets. Okay, north pole and let's say south pole. Okay, magnetic field, this is the magnetic field which is produced because of the magnets, and the loop is making some angle theta. Let's see, No force on BC and AD as they are equal and opposite. So there is no force. Okay. Force due to AB and force due to CB will be there, equal and opposite, but not collinear. Let's see. These two forces, sine component will be actually causing the loop to rotate, not cos component, because cos component though it's acting in this direction. Sine component is acting perpendicular to me. Means what I'm taking the distance, the side A distance, I'm just taking the sine component, not the cos component, because that's parallel. So the formula says F ILB sine theta. So sine component will be taking, not the parallel component. The torque is less than the case one, as in decreasing in the direction of perpendicular distance. So the torque, the value of torque will be less. So due to this force on AB, same formula A by 2, but the sine component I'm just taking. Similarly, force due to CD, same formula A by F20 A by 2, sine component I'm just taking. I'm just adding IAB sine theta I'm getting. That's torque is nothing but what? IAB sine theta for one loop. If you have multiple loops, just multiply with n. And one more important formula, magnetic moment. What is magnetic moment? Current into area of the loop. Okay, current into area, magnetic moment. This you might have seen from the mobile coil galvanometer from current electricity. So that formula only, current into ampere, sorry, area of the loop. For n loops, multiply with n. So in vector form, you can just write torque is equal to IAB, right? IA is what? Magnetic moment. M cross B. That's it. MB sin theta you can have. So some special cases when magnetic moment and B are parallel, so there is no angle making, right? When the plane of the loop is perpendicular to the magnetic field, there is no angle. How? Visualize it. If you have a plane of the loop like this, magnetic field is produced. The area vector will be like this. There is no angle, right? But when M is anti-parallel, when the plane is parallel, magnetic field is in this direction. But if you have a plane like this, there will be some vector, right? So it's making an angle 90 degree. So in that case, maximum torque will be produced. Here, torque they are talking, not force. Okay. So that's it. So I have covered almost most of the concepts from this chapter. So what you can do is, I'm not attaching the PDF for it. The reason behind is you have to write down everything in your notes. If you write and study, everything will get registered in your mind. So after that, what you have to do, you have to go and solve some questions. Simply studying these topics, remembering the formulas concepts is enough for NCERT. But even NCERT, they are asking numericals, right? So go and practice numericals from NCERT textbooks. And if you have any standard reference books or coaching materials, you solve those questions and directly you can jump to PYQs for mains and NEET preparation. I'm talking about JEE mains. Because most of the topics, let's say for example, this formula is not given in NCERT. I have taken from SL Arora, and even my coaching, they have discussed this formula. I have taken from those resources, some special cases, and here and there some points not given in NCERT. That's it. Remaining everything is from NCERT only. Okay, don't differentiate your preparation for board as well as NEET and JEE. If you study physics properly, you can able to tackle any kind of questions. That's what the complete concept I have covered, right? I hope this will be helpful. Now, for much more clarity, you can actually go through your NCERT textbook or any reference book if you have SL Arora, Modern ABC, or any standard textbooks like HC Verma, DC Pandey, or any coaching material. Refer it, refer the notes also. Note down the formulas, or you can write down the notes in your own notes itself. This will be very helpful for your revision purpose. Make a separate formula sheet, note down all the formulas here. Just take this formula, some special cases. Just take this formula, special cases. Note down this point, take this point. Okay, just note down it's moving in a circular path. So centripetal force will be equal to magnetic force. So note down the radius formula. Because in mains they may ask you the radius. What like for example, they will give you a scenario like if a charge is moving in this direction, calculate the radius. You can directly apply this formula, or you can just put this equation, then derive radius. In NEET and all, they will give direct formula based question. But in mains, you need to understand a little bit. For that, you need a lot of practice basically. That's it. Remaining concept though, everything is same. Nothing varies. You take any previous year question, this formula you have to remember. If anyone is asking you, you have to tell mu naught times of, if anyone is asking you, what is the magnetic field on the axis of a circular current carrying loop? If the distance from the center is x, radius of the loop is, or you have to tell mu naught times of I into radius square divided by 2 times of x square plus r square whole power 3 by 2. Remember this. Similarly, ampere circuit theoretical concept and solenoid, toroid. Okay. Mm, Magnetic force between two parallel current carrying conductors, very important. Conceptual too, and the torque. That's it. So complete chapter I have thorough and I have covered for you. I don't think so. Like this, a proper notes you will get in YouTube or any internet. Means handwritten notes. Because as a student, I have experienced a lot, and I know what a student will face during his or her preparation. A proper notes they won't get proper explanation for this notes. So complete thing I have given in this video. So make utilize of this. And in future I will be posting many videos related to competitive examinations. Even if you want, you can just comment it out. I will try to put some problem solving sessions for also. Okay, so slowly I will be uploading some other chapters too. Okay, side by side I will also upload some problem solving sessions, right? So if you like it, if you like this video, subscribe it, share it among your friends so that it will be useful as exams are approaching, right? Your mains first attempt is approaching. Okay, yeah, all the best. Bye.